Hey, so here we're looking at problem 10 from section 1-2, and we're asked to do the following. It says that we want to use this direction field to draw some solutions and then try to give a general solution in terms of a formula, and then we can substitute these guesses into the differential equation to see if we got them right. So the differential equation I should also include here. See that that is going to be given as y prime is equal to negative t divided by y. Now to draw a guess for a solution, I'm just going to sort of think about, well, where would I put a point to begin? Well, if I stuck a point, say right here, it seemed like it would flow up, sort of like a leaf in this water, and it seemed like the current would sort of make it flow around, kind of like this. Just a rough sketch. If I had put it down on the underside, it seems like it would flow something like that. So this is a bit of a rough sketch, but you sort of see that that seems to be the theme here. Right. The reason I'm not having it go in a shape sort of like this is that what is typically the x-axis, in this case, is our t-axis, and we typically want time to go forward. We're not very into time traveling or anything like that. So when we draw these solutions in this direction field, their solution is going to go from left to right. So these seem to look kind of like semicircles, right? That's just a guess of what it would be. So as a guess, you might say, well, the solution, well, what is a semicircle? What's the equation of a semicircle? Well, you might have y being the height. If you don't recall it, you can think back to the equation like y squared plus x squared equals your radius squared, right? These are circles that are centered at the origin specifically. Now, in our case, though, we don't have an x, but we have a t. And instead of writing r, I'm going to write some sort of constant, because whatever number you want to plug in, see. So if I were to solve this for y, I'd get y is equal to the square root of some constant squared minus t squared. It could be plus or minus. Right, so either one of those works. Now what's kind of interesting to recognize is a constant, an arbitrary constant squared. Well, if it's 3 squared, I could have just picked 9. So I could also have written this as simply c minus t squared. That's a very common trick that we're going to see is when you do some sort of operation on an arbitrary constant, we may just replace it and just call it c, since it's still arbitrary. So these seem to be good guesses, the positive version or the negative version, either one. So if we're going to substitute it in, I'm going to go ahead and just take the positive version. So let's check. So to check this solution, I'm going to need to take a derivative to find out what y prime is. So if this is, so let's write it this way. So y is equal to square root. I'm going to, for simplicity, do what I just mentioned. Just call it c minus t squared, and I'm going to take a derivative of this. So a good thing that I like to do is when I want to take a derivative of something with a radical, I like to write it in the form where the square root takes is an exponent of 1/2. So if this is my y, then to take a derivative, y prime, the 1/2 comes down, and then we're left with c minus t squared to the negative 1/2, right? Subtract off 1. But here we have a chain rule. So we would also need to multiply that by the derivative of what's inside. So that would be multiplied by, so that's a constant, so we ignore that. So we just have this negative t squared, which gives you negative 2t. So doing some simplification here, the 2's look like they're going to cancel. And so what we have left is a negative t. And this term right here, I'm going to put in the denominator. All right, so c minus t squared to the 1/2. But notice what's down below in the denominator is in fact just our y. This is negative t over y. So this tells me that when I take the derivative of y, I end up with negative t over y, or divided by y, which is exactly what our equation was in the beginning. So that means this was a good guess.